in the second hour for some problem exercises. Okay. All right. So we are here the last time. Oh, here actually we have discussed this extraction steam turbine. So we are right now here. Yep, correct. Is it? No, no, this one. There you go. Okay, so yesterday we have seen how we design a cogeneration system using a simple back pressure turbine. Now, another design, similar design, uses an extraction steam turbine instead of a back pressure steam turbine. The main difference between these two are where we get the bypass steam from. Okay, so if we use back pressure turbine, then the bypass steam that we use to control the steam flow rate. Okay. Now remember again, the reason why we need this type of control system is that this cogeneration system produces two things, right? Power, electric power, and also heating steam. Okay. Now the balance between power requirement and steam requirement by the process might change with time. Okay. So if the process requires more heating steam, then more steam should be diverted here. Conversely, if the process needs more electric power, then more steam will be diverted here, or this valve will close. Will close more. Okay, so because the turbine is a back pressure turbine, then the steam cutoff, the steam bypass, is located here. Okay, in the upstream side of the turbine, right? Now compare that to this one here. This is an extraction turbine, as you have by now. You should be familiar with the design. Okay, so the high pressure steam comes to the first expansion stage in the turbine, and then the extraction steam here. Okay, so before the steam enters the second stage, some of the steam is extracted out or bypassed out of the turbine, okay, and this will become the heating steam, the thermal steam, okay. And then the remainder of the steam enters the second expansion stage of the turbine, and together, stage 1 and stage 2 here produce the electric power, okay. And then the exit steam from the second stage is if the temperature matches, then we can also certainly use this one also for process heating. Okay. So if the steam requirement increases, the steam extraction, this one, right? The steam extraction. By steam extraction, it means this one here, this line. This is also increased. Okay. The condition of the first steam entering turbine is important in cogeneration. The steam must have sufficiently high pressure and temperature. Okay. So this incoming steam, this inlet steam, needs to have a relatively high pressure and temperature because the extract steam will be used for heating. Now, this is a very important concept. So, and this is a very simple concept that you have learned in thermal and also in heat transfer classes. Okay, so in order for any heat transfer to occur, there has to be ... What? Can anybody remember?
In order for
yeah,
a difference in temperature.
Yes, correct, 100% correct. So you need to have a delta T. You need to have a different a temperature difference between the heat source and the heat sink, right? So if you want to heat up a process stream from some temperature to a target temperature, then you better be sure that the steam temperature is larger, is always larger, larger than the outlet, than the target temperature of the process stream. Okay, and that is the reason why the inlet steam condition is usually has high pressure and high temperature. Okay, because we need the temperature, not only the mechanical energy of the steam, but we also need the temperature to be sufficiently high that it can then be used to heat process streams. Okay, and this implies that the boiler that's used to supply this HP steam, high pressure steam, must be able to produce steam at high pressure and temperature. And usually this comes at the expense of capacity. Okay, so you can imagine, right? Higher pressure, higher temperature, meaning more expensive materials of construction, thicker steels and things like that. So the bigger, if you want to build a boiler that is high pressure, high temperature, high capacity, it will be very expensive. So typically this one, if we want to produce extremely high pressure and temperature, then the boiler capacity is usually sacrificed. Okay, all right. So and by the way, guys, what I'm also hoping you guys to start to appreciate is that designing a chemical processing plant is really an open-ended problem. There's no single solution. Okay, it really depends on and on your design philosophy. If there's any specific needs or specific constraints, for example. Let me give you a simple example. Okay, now I have just asked you a few minutes ago, okay, 1 minute ago, what is required to ensure proper heat transfer? And Kevin said, okay, we need the presence of delta T, 100% correct. But if I were to ask you further, so what delta T you guys prefer? What is the value of the good, quote unquote, good delta T? Can anybody answer? And from which class you received that information?
Sir, may I answer, sir?
Mm-hmm.
That allows a high rate of transfer, of heat transfer, sir.
Yeah. So, but what is the delta? What is the value of the delta T to ensure heat transfer?
Maybe quite different, quite significant, sir. A significant difference, sir.
Yeah. Do you have a rule of thumb?
I have no idea, sir.
Okay, so again, this is a very simple question, right? Okay, so let's say that you have a process stream that needs to be heated up to 100 degrees Celsius. Okay, so that's your heating target, right? So obviously you need a heating media that with the saturation temperature, okay, meaning the condensation temperature, okay, of the steam has to be higher than 100. So you can obtain an effective heat transfer rate. Okay, so remember again, let me repeat my problem. So you have a process stream that is to be heated up to 100 degrees Celsius. Okay, so that is your target outlet temperature for your process. Okay, so it means that your heat transfer media or your heating media, the temperature has to be always higher than 100 degrees Celsius. Otherwise, you will not induce a heat transfer, right? And if that heat transfer media is a saturated steam, then its saturation temperature will have to be some degree Celsius higher than 100. Now, how much higher? 5 degrees, 10 degrees, 15 degrees. So you can easily see that this immediately becomes an open-ended problem. And this is what the typical job of engineers is. Okay, so in many cases, okay, you guys have an option. You guys have a liberty about what delta T to pick. Okay, in some cases it might be constrained. Okay, in some cases it might already be dictated by the availability of the hot stream. Okay, but in other cases you have the liberty to choose whatever delta T that you want. Okay. So, and that's a very, very typical way of, there's a very typical job of engineers. We deal a lot with open-ended problems. And personally, I think that makes life much more interesting than just closed-ended problems where you don't have any options for the solution. Okay. All right. So in this case, Depends. There are some rule of thumbs. Okay, if you read some books, it will give you a rule of thumb or a minimum. Okay, minimum, not just the delta T, but minimum delta T for a good heat transfer rate to be 10 degrees Fahrenheit. Some people say it's 10 degrees, 10 degrees centigrade, 10 degrees Celsius. Okay, so you can use either way. It's good whenever you quote numbers like that. It's good if you show whoever's asking you the reference. Okay, so if I'm asking you, okay, Pak Miki, I'm using this reference book, okay, this plant design handbook, blah 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 blah, and it tells me that a good practice is 10 degrees something. That's fine. Okay, it means that you have adopted what we call best practice. Okay, best engineering practice. There's no science for it. The science only calls that, okay, it has to be, as Kevin said, it has to be reasonably, quote unquote, reasonably high. But what is reasonably high? Is it 10 degree, 20 degree, 15? So again, just a simple rule of thumb is it's either 10 degrees Celsius or 10 degree Fahrenheit. Of course, if you go with 10 degrees Celsius, you will end up with higher delta T, right? Okay. And again, every engineering decision will have its advantages and disadvantages. Okay. Deciding to go with higher delta T will have its pluses and minuses. And you need to be aware of what are the minuses and what are the pluses if you increase the delta T. Okay. So do not forget when you design your plant next year. Okay. So if you have a job, if you have a process heating job task, okay, so you need to be aware that if this is your target process temperature, your heating media has to be higher. It has to have a certain delta T to ensure a good heat transfer. Okay. And if your heat transfer media is steam, remember, steam needs to be transported in superheated state, not in saturated state. Yes, when it enters heat exchanger, when it's about to do its heating job, then it has to be de-superheated. That is correct. But in the steam header itself, the steam condition has to be superheated. Otherwise, it will cause corrosion. Corrosion, water hammer, and all kinds of nasty things in terms of materials of construction and also fluid mechanics. Okay, so you have to increase the temperature a little bit more. Okay, so if this is your process target temperature, this is your saturation steam temperature, right? And then your superheated steam temperature, aka your steam header temperature, has to be even higher, further higher, to ensure there's a good degree of superheat. Okay, right? So that's how you design a steam system. Okay, and then that will determine your boiler pressure and temperature. Okay, and life will get even more interesting if you have multiple targets, right? Some process stream requires heating to 100 degrees Celsius, some requires 80 degrees, some requires 200 degrees perhaps. Okay, so you have to think your way through, you have to think really carefully about how you design your boilers. How many boilers are you going to build? Okay, how many steam headers are you going to build? How will you decrease the pressure and temperature from one header to the next one, to the next down, to the next level down? Are you going to just use a throttling valve, okay, pressure reducing valve, or are you going to install a turbine like this, for example? Okay, so there are there are infinite number of solutions actually. That's an engineering job. Okay. All right. So that's still ideal, but of course, when you go to real life, then you have to be grounded to reality, right? So okay, all of these calculations are nice, but when you when you're trying to build an actual chemical processing plant, you have to abide by, you have to obey what? let's say that you calculate some turbine specs. You calculate the turbine pressure, ASR, TSR, the design. So in other words, you calculate the specifications of turbine based on your on what you have learned in this class and also in thermodynamics class. And now you want to buy this turbine, right? You want to go to vendors to buy this turbine. Then reality hits you. Okay, so when you want to buy this turbine, what constraint that you need to consider? This has nothing to do with chemical engineering. It's simple logic.
Cost, sir.
Cost. And let's say you want to buy something. You open Bukalapak. Okay. And so let's say you want to buy some aquarium pump, for example, in Bukalapak or in Tokopedia. So will you always find what you're looking for exactly in terms of power, for example? Let's say that you're looking for, based on a calculation, you need a pump with a power of 36 watts. Can you find a pump with a power of 36 watts? You may or you may not. It really depends on the market. So it depends on the availability of your equipment that matches the best your specifications. So if your specification calls for 36 watts and you don't find any pump in the market that rated at 36 watts, find something a little bit higher. You can probably settle with 40 watts. But for sure, you cannot settle with 30 watts because it will be lower than your spec. Okay. So again, that's how we engineers work. So all of these calculations are theoretical. Everything that you learn in your neraca massa dan energi, in your unit operations class, everything, all those are theoretical. Okay. All those are ideal. When you want to execute a project, when you want to build a plan, you also have to look for what's available in the market. Okay. So that is when our creativity as engineers must be toned down. Okay. Right. Let's say that your McFlow calculation calls for some a pipe diameter, an ideal pipe diameter of, let's say, maybe 11.5 centimeters, the diameter of the pipe. And when you look for that kind of pipe in the market, you don't find any. What you find are 10 centimeters and 11 centimeters. So now you have to decide which one to choose, because clearly custom ordering pipe just for a chemical process plant doesn't make any sense at all. Okay. So you have to, again, you have to adjust yourself to whatever's available in the market. Okay. Oh, you can probably hear a helicopter from my microphone. My house is located near landing approach to Hussein Satranegara. I'm located far from Hussein, but my housing complex is located right at the approach path, glide path, if an airplane is approaching Hussein. So it can be a bit noisy. All right. Okay. So really, I think this is what makes, you know, hidup as an engineers. Okay. When you have these open-ended problems and you have to sort of harmonize whatever theoretical calculation result that you obtain from your HYSYS, from your calculations. You have to match that with what's available in the market. Okay, that what makes very interesting. What makes engineering very interesting. Okay, and very down to earth, I should say. Okay, all right. Okay, and this one, I think I don't have to go through much detail here. You can follow the TS diagram on the right hand side quite easily. This is just an example of how we describe a cogeneration cycle in a TS diagram. Okay, you can easily follow. You can follow the numbers here. So now this is a rather complex cycle in the sense that you have branching offs of streams. Okay, so for example, stream number 1 is branched off to streams number 2 and 3 at the same thermodynamic condition, but different flow rates and so on. Okay, and then you also have joining of more than one stream. Okay, for example, stream 9 and stream 10 now feeds into stream 11. Okay, so you can look at it, you can look at how those conditions are depicted in the TS diagrams. It's very interesting. Okay. Again, I will not go through much detail here. You can this, and the problem description is very clear. Okay, so it's not asking you to perform any calculation. It's just, you know, what I want you guys to learn here is how to describe this cogeneration cycle in a TS diagram. Okay. All right. Okay, the next one, cogeneration using gas turbine. This is actually very popular. Okay, gas turbines are operated at high temperatures, so their stack gas is still quite hot. It still contains a usable amount of sensible heat. Okay, and the thermal energy in this waste gas can be utilized by several measures. Okay, for example, we can use. Sorry, I forgot to override the Indonesian notations here. So we are talking about this exhaust gas here at this point. Now, remember, at this point, the hot gas has already done its job, expanding, turning the turbine and compressor. Okay, so here this is this gas this is a waste stream. This is a waste gas. Jadi ini gas buang ya, karena gas ini sudah menyelesaikan tugasnya, ya, sudah menyelesaikan tugasnya memutar turbin dan kompresor serta menghasilkan daya listrik. Jadi ini sebetulnya tinggal dibuang aja. Ini gas buang, nggak bisa dipakai lagi. Ya. However, again, remember, because we want to save energy, we want to save the environment, we want to extract as much heat as possible from this hot gas. Okay. And again, what uses what can this hot exhaust gas be used for? First one, and this is actually already very, very common these days for industrial GTs, gas turbines, which is combustion air preheating. Okay, so the incoming air to the compressor, before it is being compressed, it can be preheated by the hot gas, by the hot exhaust gas. Okay. Second use is for indirect process heating using heat exchangers. So this hot gas, you can use this hot gas in heat exchanger, okay, silent tube exchanger or heat exchangers or what have you, to heat up process streams. Okay, again, that's also practiced quite a lot. It's nothing novel. It's quite conventional actually. Or if the temperature is still very high, you can probably still use it to generate at least low pressure steam. Okay. Maybe in some cases you can generate medium pressure steams, okay, but certainly you can generate LP steam using this gas, this hot gas. So because the temperature is still high, for example, here, this is, again, remember, please, this is just an example, okay. So the temperature is still above 500 degrees Celsius, so we still have a worthwhile temperature. So this hot gas can be used to boil water to generate steam using WHP, okay, right, waste heat boiler. Okay. Steam generated by the WHP, if the WHP can generate steam at sufficiently high pressure, in fact, we can use the steam to drive steam turbines. Now that becomes not cogeneration, but that becomes combined cycle. Okay, because we can use that scheme to produce electricity from the GT and also from the steam turbine. Okay, so that, in a sense, that's by definition, it's not cogeneration, but that's combined cycle. Okay, but if you use, okay, if you use the steam for any other purposes aside from power generation, then it is a cogeneration. Okay, what if you have both? Okay, what if you have what if this steam, this WHP, produce enough steam that the steam produced by the WHP can be used both to produce electric power and for process heating. then what is the name of this animal? Jadi binatang namanya apa? Okay, then the name is simply combined cycle cogeneration. Okay, right, and that exists. Plants like that do exist. Okay, all right. Integrated, sometimes nama kerennya seringkali integrated combined cycle cogeneration power plant. Okay. All right, so again, it really depends on the situation. It really depends on the philosophy of the design criteria. Okay, so again, this makes life much more interesting because you have many choices. Okay, GT is so GT is an industrial term for industrial lingo for gas turbine. Okay, so a GT is generally regarded as a responsive prime mover. This is not primary. Okay, that's prime mover. Responsive meaning you can the gas turbine can follow load fluctuations very well. You can increase the RPM or decrease the RPM considerably compared to steam turbine. Okay, so therefore a GT is suitable to handle large swings of power load. Okay, now if the GT is combined into cogeneration, then energy utilization of the GT system is expected to be even more efficient. Okay, so this has become a trend. Okay, in power plant designs. We see more and more cogeneration power plants being built in Indonesia. So not just a simple GT, but the GT with a cogeneration or even combined cycle technology attached to it. Okay, because again, for the same amount of fuel consumed, you can generate more energy. Okay, you will get better thermodynamic efficiency. Okay, this is an example of a gas turbine system with WHRSG. Okay, waste heat recovery steam generator. There you go. Okay, WHRSG. Okay, waste heat recovery steam generation. Okay, right. So this is the, let's see, where's the GT? This one is the GT actually. Okay, so this small box here is actually the gas turbine, the GT. This is the, oh no, this is the inlet filters. Okay, so this is the air filter for your GT. Okay, and this is exhaust bypass. Okay, so in normal operation, this only allows a small amount of exhaust gas or even closed totally. Okay, this is there's a flow diverter here that directs the flow of hot gas, and this one is the boiler. Okay, this trapezoidal shaped box here. So this is the boiler. Okay, this is the steam boiler that utilizes the heat from the exhaust gas to boil steam, to produce steam. Okay, so pretty nifty. Okay, now whether we call it a combined cycle or a cogeneration really depends on what we use the steam for, right? Obviously the GT is used to generate electricity. Okay, but the steam, okay, the steam can be used for everything. You can use, if you have enough steam, or if you have a great requirement, an urgent requirement to produce as much electric power as possible, then you might use this the steam generated here to drive steam turbine. In that case, this will become a combined cycle power plant. Okay, but if the steam generated by the boiler is used for process heating, for thermal steam, then this will become a cogeneration. Okay, and if the steam is split into two groups of applications, again, some of the steam is used for thermal heating, some of them for to drive turbine for power generation. Then you have, cogeneration combined cycle. Okay, So you can have both actually in one process plant, in one power plant. Okay, the next one. Sorry, how much time do I have left? Okay, a little more than 15 minutes. That should be enough. Okay, the next one is cogeneration using diesel engine. This is not very common, okay, but it has been done. Yeah, we expect that there might be there may be more applications of such technology in the future. Okay, so diesel engine is a prime mover with relatively high thermal efficiency. Now, that's good, but also bad. Okay, so higher thermal efficiency means the engine, the diesel engine itself, produce a higher amount of power per liter of fuel compared to, for example, gas turbines. But because it has high thermal efficiency, it also means that the exhaust gas from the diesel engine is not very hot. Okay, so so this high thermal efficiency of the engine, of the diesel engine, means that its exhaust gas is not very prospective for further use. Ya, jadi karena efisiensi termodinamik dari mesin diesel itu relatif tinggi, bagus sih untuk mesinnya, ya. Tapi artinya gas buang dari mesin diesel itu tidak terlalu panas. Jadi sebetulnya gas buang mesin diesel ini nggak menarik-menarik banget untuk dimanfaatkan lebih lanjut dengan teknologi cogeneration atau combined cycle, gitu maksudnya. Ya. Oke, jadi diesel engine at full load typically exhibits the following energy balance. Okay, so from 100% energy contained in the fuel, it will be converted to 39.2% will be converted to shaft work. 33.2 will be ejected to the atmosphere as sensible heat and stack gas and so on. So remember what we discussed yesterday. A convenient diagram to describe this type of energy balance is called what diagram?
The Sankey diagram, sir.
Yes, you can easily plot these numbers in a Sankey diagram. Okay. So we have losses, heat losses to the environment, and so on and so forth. Okay. So steam produced by diesel-based waste heat recovery steam generator, okay, WHRSG. Again, let me repeat that. This is a lengthy abbreviation. Waste heat recovery steam generation, okay. Now, okay, so the steam produced by this system has low temperature and pressure, and this is dictated by the temperature of the exhaust gas from the diesel engine, which is also not very high. Certainly, it is much cooler than the exhaust from gas turbine. Okay, so this limits the use of waste heat only for direct heating. So the heat contained by the let me ask you a simple question. Okay. Let's say that we have a large molar flow rate of diesel exhaust. Okay. So in terms of heat flow, Q, okay, Q heat flow, yeah, key, yeah, you will get the big number. All right. Okay. Because the flow rate, the volumetric or the molar or the mass flow rate is high. So you get a large number of Q, heat flow rate. But when we want to decide what to do with this exhaust gas, we also have to be concerned with its what? With its ... The first one is, of course, as I just told you a few seconds ago, we need to check what is the heat flow, ya, berapa laju panasnya dari gas buang ini. Kalau kita ceritanya gini nih, kita punya sumber panas nih ya, mesin apalah, mesin gas, mesin diesel atau mesin gas turbine, whatever. Oke. Jadi ceritanya kita mau memanfaatkan gas buangnya untuk keperluan yang lain. Kita ingin mengambil energi dari gas buang itu, ya. Oke. Jadi pertama yang kita cek adalah Q-nya dulu, heat flow. Ya, laju panasnya berapa sih? Worth it nggak untuk dimanfaatin? Ya, is it worthwhile to be reused for other purposes? That's number one. Number two is we also need to check what of the exhaust gas.
The contents here.
Yeah, can you be more specific? What about the content?
Like how much of a certain molecule is inside the flue gas?
That usually ties with the heat flow, okay? Because heat flow depends on the mass flow, on the molar flow and the composition. But you're not entirely wrong there, because we need to be aware of what's in the gas, of course. Okay, how much water, how much, what is the moisture content, what is the dew point, because that will lead to corrosion problem and stuff like that. That's not wrong. Okay, but there's another one fundamental thermodynamic property, or thermodynamic or state variable, that we need to be aware of before we want to say, we want to jump on the wagon, okay, and say, okay, let's use this gas. Okay, and that is, the gas is this one.
Sir?
Yeah.
Is it the, I don't know, I'm guessing thermal conductivity? Like how good is it at transferring the heat, or?
Yeah, if you really want to nitpick, yeah, you can. It's usually tied to the overall heat transfer coefficient, which is quite typical for these gases. So we in chemical engineering are usually not that concerned with that, but in some cases it might be important. If you look at the screen, you can see where my cursor is pointing at. Yeah, the temperature. Okay, now just because a gas contains a lot of Q, contains large heat flow, okay, it doesn't mean it is a good heat transfer media. Remember, if you want to induce a heat transfer, if you want to heat up a process stream using an exhaust gas, a waste gas of any kind, okay, number one, you need to be sure that you have enough heat flow, okay, you know, asas black lah, Q sama dengan MC delta T itu kan ya. Oke, so delta T itu adalah apa namanya, delta T dari sisi prosesnya itu nanti menentukan beban pemanasannya di sisi proses berapa, gitu. Nah, beban pemanasannya di sisi proses ini bisa nggak dipenuhi dengan beban panas yang ada di dalam gas buang. The second one is, what is the temperature of the gas, of the hot gas? Okay. If the Q is large, if the heat flow is large, but the gas is available at low temperature, then it's not going to be very useful, right? Because you don't have enough delta T to induce a good heat transfer. And so this is what we call quality, okay? Heating quality of a process fluid, of a fluid, okay? So high temperature means high quality, high heating quality. Okay. Remember, jadi ingat ya, perhitungan heat transfer gitu ya. Jadi apa namanya? Suatu beban panas, Q ya, Q beban panas itu, suatu nilai Q itu bisa dicapai dengan memainkan beberapa variabel, gitu. Temperaturnya dinaikin, Q-nya naik. Laju alir masanya dinaikin, Q-nya juga naik pada T tetap, ya kan? Q sama dengan MC delta T, ya gitu. Jadi selain Q-nya, kalian harus lihat T-nya berapa. Kalau if the temperature of the exhaust, if the waste gas is too low, then you cannot extract the heat. You cannot obtain a meaningful heat transfer rate. Okay, so in fact, for diesel case, okay, so this rather low temperature of the exhaust gas limits the use of waste heat only for dry heating. So roughly only about 20% of the sensible heat in stack gas can be recovered. Okay, because it is already a little bit cold. Okay, it's not that hot. All right. This is an example of the use of diesel engine cogeneration for space heating in a building. Space heating itu artinya pemanasan ruangan, ya, space heating. Bukan space ruang angkasa, bukan. Space heating means that the heating is for a specific space in a building, ruang di dalam bangunan. Okay, so now, and actually this has been practiced in at least one hotel in Bandung that I remember on top of my head is Novotel. Okay, Novotel in Jalan Ciamplas. They have similar system like this. Okay, so they wait, no, that's different system. They're not using diesel engines, but they're using waste heat from their AC, from their air conditioners. Okay, anyway, same principles, different heat source. Okay, so what we have here, this is a diesel engine. Of course, the diesel engine is powered by the fuel. Okay, so it converts fuel into electric energy from through an electric power generator, of course. Okay, and then the engine will emit hot gas. Okay, hot exhaust gas. Well, as hot as a diesel engine can be, it's not that hot. Okay, and the heat, the hot gas is then used to warm up water. Okay, so this is water tank. Okay, and the water flows by natural convection through this heat exchanger, and because of the gradually increasing temperature of the water will flow that way. Okay, because it's lighter. Okay, the density decreases as the water warms up. Okay, then here we have in this tank we can siphon off, we can draw off warm water or hot water from the top of the tank. Okay, so because of the density difference in the tank, the hot water will float on top of cold water. So we siphon off hot water from the top of the tank. Okay, and we can use this for hot water in faucets, and also to heat up rooms using this. This device is called a radiator in Western countries. Okay, now we don't have this kind of heat exchanger in our houses in the tropics, of course, but in temperate climate countries, this is very common. This type of space heating is quite common. Okay, all right. So in this way, not only we can extract more energy from the fuel by using this hot gas, but we also cool down the temperature of the gas that is ejected to the atmosphere, and that's also better for the environment. That means less global warming. That means less atmospheric heating, right? So this is good. Okay. All right. And of course, because this water is only used for showers, for domestic tap water, so the temperature here is not very high. It's probably about 60 degrees Celsius. Okay, certainly not 100 degrees Celsius. You don't want boiling water coming into your body when you're in the shower. Okay, so the hot water line in shower, I think it's about 60 to 70 degrees Celsius. Okay, 80 degrees is already too hot. Okay, it's not considered to be safe for domestic use. Okay, all right. So, and then coming up to the last bit of material in this chapter, this is combined cycle. So all we have discussed so far are cogeneration. Now we can discuss combined cycle. So and a classic example of combined cycle again is using Brayton cycle as the main as the primary cycle. Okay, so waste heat recovery from GT exhaust gas can produce steam. Again, GT will produce hot exhaust gas that in most cases is worthwhile to be used for steam boilers. Okay, so the steam generated by this waste heat boiler is generally suitable for turbine drive. You can produce steam at sufficiently high pressure and temperature to be used as a motive steam. Okay, so therefore one energy source, which is the fuel here. Okay, so one energy source can be used for work generation using two different thermal cycles, Brayton cycle and Rankine cycles. Okay, So this combined cycle system improves the fuel efficiency of the overall plant utility system, obviously, okay? And it's also possible to utilize exhaust steam from the steam turbine in this combined cycle system for process heating. Like I told you, okay? So in some cases, even the steam exiting the steam turbine here, okay, is still at sufficiently high temperature that we can use it for process heating, okay, if the temperature is still reasonably high. So in this case, one energy source then produces two types of energy using two cycles. Mechanical energy produced by both cycles, the Brayton cycle and the Rankine cycle, right? And then we also have thermal energy recovered from the turbine exhaust steam from this one here, okay? This is called combined cycle cogeneration, quite simply, okay? Right? Very elegant solution, okay? Now, maybe you ask in your mind, okay, so if this is so good, how come not all of chemical processing plant should use it? This is going back again to our when we design chemical processing plants, we need to be aware of the constraints, the objectives and the constraints that's facing that design problem. Okay, so here, for example, okay, so we great, we can extract more energy from the fuel, but do we need it? Okay, do we have an urgent need to recover more energy from our fuel? Now, as cruel as that might sound, okay, there is a question that we as chemical engineers should ask. Okay, I'm giving you an example. Okay, I think I have shown you at the beginning of this semester, I think. Okay, boilers in the fate of palm oil biomass in our plantations. Okay, now a single PKS, pabrik kelapa sawit, ya, a single CPO mill typically produce much. They typically have excess supply of bioenergy, okay, for their own use. Okay, so in these plants, we only need steam to steam is needed to dislodge palm fruits from the fruit punch. Jadi steam di dalam pabrik kelapa sawit itu digunakan untuk merontokkan buah dari tandan kosong sawit, dari tandan sawit, ya. And then steam is also used to heat up the feedstock, all of the palm fruits as we expel oil from them, ya. Jadi pada saat minyak itu diperas dari buah sawit, itu juga sistem pemerasannya dipanaskan dengan steam. Ini yang akan melunakkan jaringan sel dari buah sawit dan mempermudah ekstraksi minyak. Ya. And some of the steam can also be used to generate electricity. Yeah. But an oil palm plantation typically generates much more biomass than what is required by the CPO plant to generate their energy, to generate power and steam. Okay, so in that case, and another constraint is, okay, so you might think, okay, why don't these palm oil mills produce electricity and then sell it to PLN, sell it to the grid? Now, there are some problems there, okay. The first one is the CPO mills are frequently located in remote areas, and they don't have connections to the local grid, to the local power grid. Number two, there's a regulation that says that PLN only buys bioenergy at a quote-unquote normal price. They don't want to subsidize. The government does not want the PLN. Now, I shouldn't say government. The PLN doesn't want to subsidize bioenergy electricity. So that will mean loss of money for these plants if they sell their electricity to PLN. So they say, okay, so why bother? So we're not going to produce electricity. We're just gonna use our biomass, in these cheap, although low efficiency boilers, because it's good enough for us. Okay, we can get enough steam, we can get enough electricity for our use. We cannot sell. There's no way that we can sell our electricity economically anyway to PLN. So why bother, right? So these are, again, as cruel as it sounds, this is something that you guys need to understand when you design a chemical processing plant, okay? Because you cannot change anything. You cannot change everything. Okay? You cannot change government policy. You can lobby for their support, of course, you should, okay? But we cannot be certain that we can bend the rules according to our interests, okay? Even though the interest is noble, right? Okay, so there's a lot of sides to a story. Okay, again, this is also I'm encouraging you to think thoroughly, to think on a systematic way, ya, berpikir sistem. Ya. Engineer tidak boleh berpikir dari satu sisi saja, tapi harus berpikir secara sistem. Oke, kenapa ini nggak jalan? Kendalanya apa? Ya, kendalanya dari mana aja nih? Apakah dari teknologinya, dari ekonominya, dari peraturan pemerintah, marketnya nggak kondusif? Banyak, ya, banyak sekali hal-hal yang harus kita pertimbangkan sebagai engineer. Okay? Without making you scared to make a decision. Okay, so this is just a simple parameter to evaluate efficiency that is brought about by cogeneration and combined cycle technologies. Okay, so the consumption of energy source in a power plant. Now remember, this is power plant. This is electric power plant. We're not talking about any random chemical processing plant, but we're talking about power plant, pembangkit listrik, ya, instalasi pembangkit listrik. So again, the consumption of energy source in a power plant can be stated as heat rate, HR. For electricity production, yeah, the heat rate is defined as energy contained in the fuel, okay, the higher heating value or lower heating value of the fuel, divided by the kilowatt hour of produced electricity. Okay. I think this is easy enough to understand. For thermal energy production or steam, okay, so the heat rate is defined as energy in fuel divided by the BTU in produced steam, okay, or megajoules or gigajoules in produced steam. Right. Now these equations involve efficiency of every process in power or steam production systems. So boiler efficiency, turbine efficiency, and generator efficiency is all lumped together in these quantities. Okay. HR is often used in cogeneration evaluation on the basis of thermal energy as the main product and electricity as the additional product. Okay. And the difference between fuel consumption in cogeneration and conventional production system, steam production, is called incremental heat rate, IHR. Okay, so this is HR cogeneration. So this would be the value of HR that we obtain in the cogeneration configuration minus the heating rate that we obtain in conventional steam production divided by the kilowatt hour of produced electricity. Okay, so this is the incremental heat rate. Yeah. Okay, this quantity is used to evaluate how much saving that we get by implementing cogeneration. Okay, so selection of prime mover in cogeneration. Now we have reviewed some examples. Okay, we have discussed cogeneration technology that uses steam turbine, gas turbine, and also diesel engine. Okay. So a plant's specific requirements on electric and thermal energy determines the type of prime mover selected for this cogeneration system. Okay, so again, when we design a chemical processing plant, we have to consider what is the balance. Does my process plant require more electricity as opposed to thermal energy, or is it the other way around? Or is it more or less balanced? Okay, so this will determine the type of prime mover that is suitable for the cogeneration. Okay, now let's take a look at some. These, again, I should warn you that these numbers are just examples. Okay, these are just examples to show you the point. Okay, now as an example, the ratios between electric power output to thermal energy output, meaning steam production rate, okay, steam energy output of cogeneration systems based on 3 types of prime movers are as follows. Okay, so cogeneration using steam turbine, okay, the ratio between electric power output to steam energy output is in the order of 0.1. Okay, meaning this is more suitable when the chemical plant requires more heating energy compared to electric energy. Okay, yeah. The second one, using gas turbine, okay, cogeneration using gas turbine, the ratio is 0.597. Okay, so yeah, in general, it is it still leans more towards thermal power generation, so we can get more thermal power generation as opposed to electric power generation. But now the ratio is a little bit closer to 1, meaning it's more balanced. Okay, so if your chemical processing plant more or less requires a balance, have a balanced requirements between electric power and thermal energy power, then gas turbine cogeneration might be the thing for you. Certainly, it is more suitable than steam turbine cogen. Okay. And lastly, what about diesel engines? The diesel engine, clearly when you see the ratio here, you can immediately see that diesel engine leans more towards electric power generation than thermal energy generation. So if your chemical processing plant requires more electric power and you would consider any thermal energy generation to be just bonus, okay, of some sort, then diesel cogen is the more suitable type of technology. Okay. I can name an example, okay, what type of chemical processing plant that requires more electric power compared to thermal heating. Smelters, okay, nickel smelter, for example, okay. A nickel smelter plant uses a huge amount of electric power, okay, because they have to run all sorts of electrochemical processes, okay, for the smelting operation, okay, to convert nickel ore into nickel matte. Nickel matte is a mixture of nickel, iron, and some other metals that can be processed further into high purity nickel. Okay, so because that conversion from nickel ore into nickel matte occurs through electrochemical processes, then nickel smelters require more electric power than steam heating. They need to generate steam as well, but at a much smaller quantity. Okay, right? Okay, so most chemical process plants typically use steam turbine based cogen, okay, because usually, not always, okay, I should emphasize not always, but most, okay, most chemical process plants, they need more steam heating, okay, and the electric power they get as a bonus. Okay, most chemical process plant, okay, most. While GT-based cogeneration is more popular with electrical utility companies to improve their peak shaving production efficiency. Again, this is just a rule of thumb. Okay, you should not say that. You should not keep in mind that all chemical process plants will automatically select steam turbine-based cogen. That really depends on the situation. Okay. All right, and this problem example will be reviewed by Pa Hendra. This is just some examples of cogenerations. Okay, on the left-hand side here, this is the largest container ship ever built at 156,000 deadweight tons. Okay, so this is a huge vessel. The main engine is a Wärtsilä Sulzer 81 megawatt diesel, burning more than 6,000 liters per hour of bunker fuel at economical cruising speed. And this is a ship this size, they may have more than one of these these massive diesel engines. Okay, and because they want to conserve energy on this vessel, so they install a WHRSG steam turbine, okay, attached to the diesel exhaust engine that can generate 8.5 megawatts. Not bad. Okay, it's better than just to waste all of those hot gases to the atmosphere, right? Okay, so they can claim that they have a green operation, they have a green fleet that they can take and they can take credit for that. Okay, at the very least, this is a good corporate image at the very least. Okay, but energy saving is so much more than just simply corporate image. Okay, there are tangible benefits to doing that. Okay, so again, 12% of the engine output is actually used to generate steam, and then the steam generates power. So not bad at all. Okay, hey, 8.5 megawatts. This is big. This is, this is enough untuk mentenagai 1 atau 2 RT barangkali ya. Okay, all right. And the right-hand side here, this is the Crescent Casco generation plant. Okay, and this is constructed to supply electricity and steam to Petrokimia Gresik. Okay, so this power plant produces 22 megawatts of power and 160 ton per hour of steam from this one plant. Okay, all right. And this one here, this is strictly a power plant. So this one is not a chemical processing plant, but this is pure and simple. This is only a power plant. Okay, and this is called Jawa 1. I think it should have been started the production, but I don't think it has started up yet. Okay, so this is supposed to be the largest combined cycle power plant in Southeast Asia, and so this one is combined cycle gas turbine power plant. Okay, 1,760 megawatts. It's huge. It's really huge. Okay, and this is a combined cycle. Okay? So it has gas turbines, and it also have steam turbine. Okay, to produce additional electric power. All right, any questions? If not, I'll hand over the class to Pak Hendra. All right, Pak Hendra, you can start.
Okay, yeah, okay, Pak Miki, thank you, Pak. Okay, let me continue the course materials that has already explained by Pak Miki. Yeah, maybe I will try to add additional course materials regarding the advantages and the disadvantages of the cogeneration system. So you have already learned regarding the cogenerations as well as the combined cycle. Yeah? So I'm just wondering, and I have questions for all of you. So if you can answer my questions, please, you can just turn on your mic and just state your answer. Yeah. So what after you heard, yeah, the concept or the working principles of the cogeneration systems, what do you think is actually the advantages of the cogeneration systems compared with the conventional power plant system? Anyone have an idea? So we can actually have a look through three perspectives. Yeah. So the first one is based on the, for example, economical perspective or financial perspective. Second one is from the maybe from the environmental perspective. And the third one maybe from the operational perspective. Can anyone share your thoughts regarding this? So if I write it down in here, so I have based on the financial or economical perspective. The second one is based on the operational perspective. And the third one is actually based on the environmental. Okay. Okay, anyone want to try give your idea?
Sir?
Yep.
Cogeneration has higher efficiency than the conventional.
Okay, higher efficiency. Yeah. So I think it's actually based on the operationals. So usually for the conventionals, I'm sorry, higher efficiency. Yeah. So for the conventionals power plants, what is actually the common efficiency is about, I think, 30 until 45%, which means that I think there's about 55 until 70% the fuel's energy that is not actually well utilized. Yeah. So that's why by merging the technology with the cogeneration system, it will actually increase the efficiency up to, yeah, maybe 70 until 80%. Okay, good answer. Anyone? Any other students want to share your thoughts regarding this?
Yes, sir.
Yep.
So because the efficiency also higher, so financially or economically, you are, yeah, it's better. So
Better.
like the amount of money that you use,
Okay.
it come into good use.
Okay, so in here I can conclude that you need kind of a lower fuel cost. Yeah, because when you use kind of the similar, as Pamiki stated, that when you use similar amount of the fuels, you will generate more efficiency. It means that you will save a lot of money from there. Yeah. So based on the environmental, anyone have a thoughts regarding this?
Sir, maybe
Yep.
since it has higher efficiency, then that means the energy waste is lower.
Okay, energy waste is lower.
Yeah.
Mhm. So actually it can actually reduce the greenhouse gases emissions by using this technology, by using the cogeneration system, or it can actually based on the theoretical approach, that by using the cogeneration system, it can actually reduce also the SOx emissions, especially when you use the natural gas as a fuel. Okay, but however, there is still the disadvantages of conducting the cogeneration systems. So anyone want to try or want to guess what is actually the disadvantages if we performing or conducting the cogeneration systems in the, for example, in power plant?
Higher upfront cost, sir, and
Higher upfront
maybe
cost,
higher
okay.
operational cost because it's more equipment to maintain.
Okay, higher operational costs because a lot of things that you need to maintain. Yeah. Okay. Any thoughts? Any other thoughts? So how about the demand? Yeah. So as mentioned by Pamik, the demand for the steam and electricity. So it's actually must occur simultaneously for this case. Yeah. So for example, if you produce if you produce the electricity based by using the cogeneration system, for example, there is sun being used in your, or there's actually an excess of the electricity produced. So you can actually sold it to the, for example, to the PLN or electric company. Also when heat is not actually required, and the heat produced by the cogeneration system can be used to, for example, to run the steam power air conditioning system, as mentioned by Pamiki in some of the hotels in Bandung, Novotel, they actually utilize the waste heat, in order to from the air conditioner in order to use it or utilize it in the hotel itself. Okay. Any other thoughts for the disadvantage? Maybe one more disadvantages in this case.
Sir,
Mm-hmm.
so I read again the definition of cogeneration. Does it only use waste heat only? So it doesn't mean like it's the main source?
Good questions. So in this case, what do you think? Is it only the waste heat as in this case as a source, as a source of the heat in this case?
So if
Or,
it's
or we
only
can use also a fuels. Yeah. So what kind of fuels that we can actually use it? Is it fossil fuels maybe, or a renewable energy? Okay, I think in the previous slide, Pamiki already explained. Yeah, so there is actually a lot of source of the heat that can of the fuels that can actually use. For example, the diesel. Yeah, you can use also the gas turbine. You can use also the steam turbine. Yeah, but if you use the diesel or any other fossil fuels, yeah. So what is actually the main disadvantages? So you will create air pollution, of course, yeah. Even though if you're comparing with the conventional power plant, it will generate lower greenhouse gases emissions as well as the SOx emissions, yeah. But in this case, if you still use a fossil fuels, yeah, when you burn it, combusted it, yeah, it will still generate the air pollutions, yeah, like SOx, NOx, or maybe CO2 emissions, yeah. So therefore, there's actually a lot of research is being conducted at the moment or being developed, yeah, by using several renewable energy based in here, yeah, to perform or to conduct the cogeneration system, yeah. So some of the even though the scale is not actually large enough, so this is actually mainly for the very small scale or micro CHP we call it, yeah, or micro combined heat and power, yeah. So in this case, there are 3 examples stated in this slide. So we can use the solar, so combining the solar photovoltaic electricity and hot water, yeah, in order to produce the hot water and also the electricity. Yeah. So by combining the photovoltaic electricity and solar hot water, it can actually improve around 5 times efficiency compared with the traditional photovoltaic systems only. Yeah. The second ones, we can actually use a biomass, yeah, as a fuel, yeah, and we utilize the hot gas based from the combustion chamber as heat sources, yeah, and after that we can actually use it, yeah, for the cogeneration system, yeah. So the biomass, as we know that it is classified as yeah, we call it kind of the zero emissions, yeah, or the, yeah, we can actually state it as the net emissions, because yeah, during the plantations, yeah, the biomass of course will actually capture the CO2, even though during the combustion process it will actually produce the CO2. So it's kind of the balance, yeah. So we can actually classify the biomass as the one of the renewable energy that can be used as an alternative to perform the cogeneration system, yeah. And the last one, we call it the fuel cell, yeah. So the fuel cell stack in here, yeah. So based on the reductions and oxidation process, commonly we use hydrogens as feed, yeah, and also the oxygens, yeah. So the hydrogens will oxidize to generate the H plus, and the oxygens will reduce to generate the water, yeah. And based on the reactions, it will generate the electricity as well as it will actually use it, yeah, for the cogeneration system. So this is actually just the additional knowledge, yeah, for you, because the renewable energy can be also used to be utilized for the cogeneration system. Okay, so I have one video, maybe, yeah. So it's regarding the combined cycle. So Pamiki already explained regarding the theory of the combined cycles. I think it will be better also to see the video in order to make you more understand regarding the working principles of the combined cycle. So the video is about 3 minutes, so enjoy the video. Okay, I think I didn't share the sound first. I will share the sound first. Share the sound.
Hello, everyone. My name is Jackie, and I will be your guide throughout the plant tour. Does anyone know what a combined cycle power plant is all about? Well, let me put it this way. The plant is a cleaner and efficient way of producing electricity. and even captures wasted heat and uses it to increase the plant's electrical output. Now please follow me and let's move towards our first stop. In front of us, you can see a gas turbine. This one is our 9HA. This turbine weighs approximately 400 tons, almost the equivalent weight of a fully loaded Boeing 747 aircraft. A gas turbine, the heart of a power plant, compresses air and mixes that air with fuel, which is ignited. The hot air fuel mixture moves through gas turbine blades, making them spin. The fast-spinning turbine drives a generator that converts the spinning energy into electricity. Behind the gas turbine, you can see another key component, the Heat Recovery Steam Generator, HRSG. Its mission is to capture exhaust heat from the gas turbine that would otherwise escape through the exhaust stack. Thanks to the captured exhaust heat, the HRSG generates steam where it is then delivered to a steam turbine, making even more electricity. Pretty cool, huh? We are now approaching our next stop, the steam turbine. Can you see those huge bundles of pipes running out of the HRSG? It is the main steam piping, which brings high temperature and high pressure steam from the HRSG to the steam turbine. Here we are, the steam turbine. This piece of equipment uses steam to spin the generator. Similar to the gas turbine, the high temperature and pressure steam passes through the steam turbine blades, turning the generator to make more electricity. Here we are at the generator. This is where the magic happens. The spinning of the gas and steam turbines drives the generator rotor to spin, converting mechanical energy into electrical energy. Okay, folks, let's continue our tour. Running out from the generator is the bus duct, which conducts generated electricity from the generator to a transformer, enabling the electricity to be sent to the power grid, to which we connect our home, schools, businesses, pretty much everything. The last stop of our plant tour is the control room. Everything you just saw is being monitored and controlled in real time, right from this very building. Farewell. Well, folks, this wraps up our tour of GE's combined cycle plant. It was a pleasure having you here, and we hope you enjoyed the experience. See you next time you flip on a light switch.
Okay, so this video shows that the combined cycle plant works, yeah, to produce the electricity and also captures the waste heat from the gas turbine in order to increase the efficiency as well as the electrical output. Yeah. So based on the video, just want to summarize. Yeah, quick summarize. So how the combined cycle power plant can produce the electricity? There's actually 3 ways to produce the electricity. In this case, anyone can share the thoughts based on the video. So how the electricity produced, yeah, by using the combined cycle system technology.
First is the gas turbine also.
Yes, gas turbine. It will actually burns the fuels, yeah. So the gas turbine compresses the air and also mixes with the fuels that is heated to very high temperature, yeah. And the hot air fuel mixtures will move through the gas turbine blades, making them to spin, and also it will consequently it will actually produce the electricity. Okay. The second one is gas turbine burns the fuels, yeah, in order to produce the electricity. What is the second one? The second ways to produce the electricity using the combined cycle system.
if I'm not mistaken, steam turbine gitu kan?
Yes, steam turbine, yeah. So the steam turbine will actually delivers the additional electricity, yeah. So the steam turbines actually sends the energy to the generator, yeah, where it's actually converted into the additional electricity, yeah. So what is the last one?
Is it the exhaust heat recovery, sir?
Yes, good, yeah. Exhaust heat recovery, or we call it the heat recovery system. Heat recovery system capture exhaust, yeah. Or we call it the HRSG, as mentioned by Pamiki, yeah. So heat recovery steam generators will actually captures the exhaust heats, yeah, from the gas turbine that would otherwise escape through the exhaust stack, yeah. So it will create a steam from the gas turbine exhaust heat and actually delivers it to the steam turbine, and finally it will actually generate the additional electricity, yeah, as mentioned by step number 2. Okay, so this is actually the 3 ways how the electricity can be produced, yeah, by using the combined cycle. Okay, so we'll move on. We'll move on to problem example number 1. Yeah, so this is actually one of the examples that we can actually solve it, yeah, during this final materials for today. So this is we have a turbine with the efficiency of 60%, and it's used to utilize the process steam. And the thermal energy requirements for the process is 300 times 10 to the power 6 kilojoule per minute. And the thermal energy needs are supplied by saturated vapor condensations at temperature of 259 degree Fahrenheit with the pressure of 35 psi absolute. And the steam from the boiler is prepared under the conditions P1 300 psia and temperature of 800 degree Fahrenheit, yeah, or classified as the hot steam. And the steam is flow first through the turbine so that the expansion results are saturated steam in the process heating conditions. And we need to determine the power output, yeah, of the turbine in megawatts. Okay. So how we can actually solve it? Yeah. So I just give you the short explanations how we can actually do it step by step to solve this problem. Yeah. So firstly, I think it will be better also to create, yeah, the if you face this kind of the problems, it will be better to create the the graphic plotting between the HS diagrams, yeah, or enthalpy versus the entropy diagrams, yeah. So where we have the conditions, 2 conditions, yeah. So we have condition number 1, yeah. So stated, for example, here, and conditions number 2, okay. Or we can actually put it in this case, we have pressure 1 and pressure 2, yeah. Okay, so in this case, there will be 2 points, yeah. The first points, we call it, for example, in the first conditions, yeah. The first point in the first conditions, we call it as the hot steam prior to entering the turbine. Okay, so we classified it as this one, the point number 1, yeah. And point number 2 is the conditions where the steam at the turbine, it actually expanded, yeah, with the expansions of the irreversible expansions, yeah? Or we have it something like this, yeah? Okay, so we have 1, 2 in here, yeah. Okay, so based on this, in order to because we need to calculate the output, yeah, the power of the outputs of the turbine, yeah. So how we can actually calculate the output of the turbine, so we can actually get it, yeah. So the final formula that we need to actually solve is the power equals to the mass, or the mass flow rate of the steam multiplied by the enthalpy difference, yeah. H2 minus H1. Okay, so based on this, then the first thing that you need to do is you need to find out the enthalpy, enthalpy at condition number 1 and enthalpy at condition number 2. Okay, so the first step you need to do is you need to find out the enthalpy and also entropy, or we can actually notate it as the H1 and S1. So based on this, we can actually calculate it, or you can have a look through the conditions. So we have a P1 equals to the 300 psi, and we have also the T1 equals to 800 degree Fahrenheit. So you can have a look here through the steam table for the first initial conditions. So you can have a look through the steam table in order to get the values of the enthalpy and also the entropy. Okay, so once you get this one, then you need to calculate this second one. So you need to calculate the enthalpy and also the entropy at conditions number 2. But there is actually another way to calculate it. You can actually calculate it based on the because this is actually the irreversible expansions. So we can actually do it in another way. Finding out another way to calculate the H2. So we can actually add another point in this case, where the process we call it as an isentropic expansions. And therefore the entropy at point number 1 and also at point, for example, I put it 2A in here, is similar. So we have so for condition number 2, we need to calculate the H2 and also the S2. And because, as I mentioned before, because the this is the isentropic expansions, then we can actually say that the S2A will be equals to the S1. So the entropy at condition or at the point number 1 will be equals to point number 2A. So you will get this one. And we can actually calculate it, the enthalpy at point number 2A will be equals to, by using the interpolations. So we will have the formula of this H2A minus H1 divided by the HG minus H1 equals to S2A minus S1 divided by the SG minus S1. While the HG and SG is actually the saturated vapor enthalpy and entropy respectively. H1 and S1, you already got it, from the first step in here, based on the steam table. The S2A is actually equals to the S1. Then you can actually calculate it, the H2A based on this. So once you calculated the H2A, we can calculate the enthalpy at condition number 2. So which is actually the H2 in here will be, so if we make the assumptions, sorry if too noisy, because Zizi boleh keluar lagi ngajar, boleh ya? Bentar ya, ngajar. Okay, sorry for the inconvenience. So if we actually assumes that this conditions is assumed as the ideal gas, then we can actually use the formula where the efficiency equals to the difference of the enthalpy of the enthalpy at point number 2 and 1 divided by the enthalpy of point number 2A and 1. So based on this, you can actually calculate it, the H2. Because H2A is already get it from the step number 2, H1 you already got it, and the efficiency is based on the problems is 60% efficiency. Okay, so based on this, so we can based on the problems also, it is actually assumes that the steam is flow first through the turbine. So the expansions results saturated steam, yeah, in the process heating conditions, yeah. So which means that it is actually produce the saturated steam as well as the saturated water, yeah, in this case, yeah. Okay, so after that we can calculate it, the heat that is actually released, yeah, through the condensations. Okay, but before that, you need also to find out the conditions where the water is actually saturated, yeah, or we can actually put it as the conditions number 3, yeah, water saturated. So at pressure, so where the pressure is actually 35 psia, yeah. So it's similar with the conditions number 2, yeah. So the pressure is 35 psi absolute, and also the so you need to calculate or find out the enthalpy, yeah. So based on the steam table as well. So in steam table, if you have a look, yeah, there is actually the in the steam table there's actually the enthalpy for the saturated vapor and also for the saturated liquid, yeah. So you can have a look through it in order to get the enthalpy of the saturated liquid in this case, yeah, with the pressure of 35 psia and temperature of 259 degree Fahrenheit, yeah. And after that, we can calculate the heat release through the condensations, yeah. So where the formula is actually Q equals to the H3 minus H2, yeah, or the enthalpy of point number 3, which is actually the water saturated minus the steam saturated one, yeah, or the conditions number 2. So you will get the heat release due to the condensations process, yeah. And after that, you can actually calculate the flow rate of the steam, yeah, or the M steam. Okay, so the M steam will be equals to the Q divided by the, so the Q in here indicated that the demand of the heat, yeah, the thermal energy requirements for the process, or QP, yeah, in this case, where the small q is actually the heat release, yeah. Okay, so once you get the flow rate of the steam, or the mass flow rate of the steam, then you can calculate the work, yeah, or the power, yeah, the output power. Where is actually equals to the M steam multiplied by the H2 minus H1. Okay, so M steam, you get it from here. You get actually H2 here from the second step, and H1. Yeah. Okay, so again, don't forget also to consider the units. Yeah, so please be careful of the units. Yeah, how you can because the unit in here is actually in BTU and also in degree Fahrenheit. Yeah, so usually in degree Fahrenheit, when you have a look through the steam tables, usually the units of the enthalpy is in BTU per pound. Yeah, it's not in kilojoule per kilogram. So please be careful of looking through the unit. Yeah, and you need to convert it later on to the megawatt. Yeah, in this case. Okay, so this is actually the examples that you can actually find out in Paheri dictate books, yeah, or the materials books from written or the author of Paheri. Yeah, so you can have a look. This is actually the examples of 8.1. Yeah. It's actually one of the examples how we can find out the power output, yeah, based on the turbine efficiency and also yeah, based on the steam flow rate as well. Okay, any questions for these problems? I know that it's actually very complicated. Yeah, it's actually a long way to solve it. But if you have a look later on through the Paheri textbook, yeah, so please you can learn step by step, yeah, how to do it, yeah, or solve this kind of the problem. Yeah.
Sorry, sir. I want to ask about the M steam, sir. What's the formula again? Is that QP over something, sir?
QP over the Q. So the small q is actually the heat release through the condensations. You get it from here. Yeah, sorry. This one. QP is actually the thermal energy requirements. Yeah, this one stated in this process. Yeah, or in this problems, which is 300 times 10 to the power 6 kilojoule per minute. Yeah, while the small q is actually the difference between the enthalpy at point number 3. Yeah, and enthalpy at point number 2. Yeah, or enthalpy 3 in here is actually indicated the saturated water. Yeah, you got it, yeah, you got it from the steam table, the values of the H2.
Sir, since its efficiency is 60%, do we multiply 60% to QP, sir?
Wait. So you mean the heat release? Is it correct?
There's an efficiency in the question, sir, somewhere.
Yeah. The efficiency is actually used when you calculating this one. Yeah. So when you calculating the H2. Yeah. So the efficiency is equals to the, if we assumes that the gas is actually, or the condition is actually similar to ideal gas. Yeah. So you can use this formula where the efficiency is actually the difference between the enthalpy. Yeah. So the enthalpy of here and here divided by the enthalpy of the H2A and also L1. So you actually use the enthalpy in order to calculate the enthalpy of the enthalpy of the point number 2 in here. Yeah.
Okay, sir.
Okay.
So, sir, what you will be given is 0.1, right? So 0.2 won't be given, right?
Which one?
Wait.
Sorry.
Wait. I'm confused.
Yeah. So the H1 and S1 you get it from the steam table. Yeah. So by have a look through the conditions, operations conditions, which is in 300 psi absolute pressure and 800 degree Fahrenheit of the temperature. Yeah. While the H2 and S2, yeah, you can calculate it, yeah, based on this formula. Yeah. Once you calculated the H2A, yeah. Once you calculated the H2A by using the interpolations process, yeah, the S2A you can actually get it based on, because this is the isentropic. Yeah, so isentropic, it means that you will have the similar entropy values S and S1. So you can put it S2A equals to S1, while the SG and also HG is actually the saturated vapor enthalpy and entropy. You will get it also from the steam table. Yeah. While the S1 and H1 you get it from the first step. Yeah, and you can calculate the H2A. Yeah. So once you calculate the H2A, you can calculate the H2 by using this formula.
Okay, sir. Another question, sir.
Yep.
In the HS graph, how do we determine the line for line 1 and line 2, sir?
Yeah. It's not given in here. Yeah. There should be the conditions or the process. Yeah. So this must be stated that the process is actually non-reversible expansions. Yeah. So if non-reversible expansions, it means that the process or the profiles, yeah, of the condition 1 and 2, it will be something like this. Yeah, the profile. If it's actually non reversible expansions. Yeah. While in order to make it easier to calculate the enthalpy at conditions number 2, we can actually use this way. Yeah, in order to make it easier to calculate the enthalpy of the point number 2. Yeah, so we can assume that there's actually another point in here, which is 2A, and it's actually isentropic expansion system. Yeah. And after that, yeah, we can actually calculate it by using the formula of the efficiency. Yeah. That should be stated in the problems actually. Yeah, whether it's actually the expansions is adiabatic, non-isothermals, yeah, and non-reversibles, or maybe isentropic expansions, yeah, and so on. It must be stated in the problems or in the questions. Is it answering your questions, Kevin?
Yes, sir.
Okay.
So, but sir, so will the line be given, sir?
Huh?
Will the like the line 1 and line 2 will it be given, or should we like draw it ourselves?
Well, it actually depends, yeah, depends on the depends on the yeah. I don't know, maybe for the exams or quiz, maybe, yeah, the process, I think the process will be actually stated, but I'm not sure whether the graphic, yeah, or the HS profiles for each conditions will be given or not, yeah. But yeah, you have to you have to understand also, yeah, how we can actually draw the line, yeah. Okay, Kevin.
Yes, sir. Thank you, sir.
No problems. Any other questions? I think it's already 7 to 4, 7 to 5 now. If there is no questions, I think I will end up this course. Students, any other questions from the students? Please have a look through all of the exercise, yeah, or all of the examples in the Paheri textbook, yeah. So I think there are around 4 examples, yeah, of the problems. So another examples is actually regarding how we can calculate the increment heat rate, yeah, as mentioned by Pa Miki. I think in example 8.2, there is actually a way we can actually compare the conventional power plant system and also with the cogeneration system. So we can use the IHR formula to calculate or compare the efficiency between the conventional and cogeneration system, yeah. And another example is in 8.3 and 8.4. There are actually another applications, yeah, on how we can calculate the efficiency. Okay, any more questions from the students before I end up?
Sir, I'd like to ask regarding the UTS dual schedule, sir. Is it in 2 weeks?
Pak Miki, can you confirm regarding the mid-exam too, Pak? Because I didn't get the information yet from Pak Heri and team in the regular class. The committee still here? Oh, it's already. Oh, committee. Okay, I think committee is started. I will let you know as soon as possible. I will try to ask to the lecturers from the regular class, yeah, regarding the mid-exam 2, yeah, and yeah, we'll let you know soon.
Okay, thank you, sir.
No problems. Any other questions? Okay, so if there is no more questions, don't forget to fill in the attendance list, yeah, in CX, and I will end up this course. So we'll see you again on Wednesday, yeah, from 8 to 9, and we will continue our course material regarding the electricity, yeah. Okay, so thank you very much for your attentions and for your actively engaged in this class for today, and we'll see you again next week. Yeah, stay safe and healthy, everyone. Bye-bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Problems.